Hello, good morning, everyone. Dr. Mansi has joined. Dr. Mansi.
Yes, ma'am. Hi, good morning.
Okay. So we'll just start in 2 minutes.
Yeah, sure.
So a very good morning to everyone here. Dr. Mansi, our participants, everyone present here. Actually, today's session was, and I welcome you to the day 9 of our add-on course on basics to advances in bioinformatics. And we had our speaker, Professor Latha, but due to some unavoidable circumstances, she was not able to join. And we have with us uh, Dr. Mansi P. Karwal, who is PhD scholar under Dr. Latha. So, I would like to welcome Dr. Mansi, and before that, I would like to introduce to the speakers. Dr. Mansi P. Karwal, she has done her BSc in Biomedical Sciences from Shahid Rajguru College of Applied Sciences, Delhi University. She has her MSc in Bioinformatics from Jamia Millia Islamia and her PhD in Biochemistry from University of Delhi. And her expertise is in bioinformatics, and her research work is primarily focused on CADD and immunoinformatics. So, with very short introduction, I would not like to take much time and would like to welcome Dr. Mansi for today's session.
Thank you so much, ma'am. Thank you for this. I would like to welcome all of you, and I hope my voice is clear and audible before we can
Uh,
begin.
it is audible, Mansi, but I think it's a little bit slow. I mean, it can be louder, I
Okay,
guess.
I'll try to be a
You
bit
can
more louder.
स्पीकर को थोड़ा सा पास कर सकते हो.
Yeah, okay. So, is that better now?
Yeah, it's okay now.
Yeah, okay. So, thank you everyone, and I hope you're having a great time in this workshop, which is being conducted by Tabassum ma'am and Dr. Ruchiveer. And I would like to thank Dr. Latha for giving me this opportunity to do this on her behalf today, as she is really busy and occupied with some work. So, let's begin with computer-aided drug design, the topic for discussion for today. And I'll give you a very brief overview of what we're actually going to do in today's session, and then we'll have a good hands-on session in the coming time. So I'd first like to share my screen, and I'll just give you a brief overview of what we're going to do today. So, okay, so is my screen visible?
Yeah, it's visible, but you can make it full screen, Mansi.
Yeah, ma'am, actually, there are a few slides in between, so I just thought that I'll show it like this.
Okay, fine, it's up to
Yeah,
you.
okay. So, computer aided drug design is one of the most important fields in bioinformatics, basically because the time needed to procure or design any new drug is extensively large, and it takes a lot of years and a lot of money is involved from the target discovery to the drug coming to the market. Approximately, if someone follows the experimental path, it would take nearly 10 to 12 years for someone to get a new drug to the market, and the cost involved is approximately 2.6 to $3 billion. Now, when this drug comes to the market, there are a lot of steps in between that are involved, beginning from the discovery of the disease, the proteins or the targets that need to be worked upon, the drugs which need to be worked upon, following clinical development stages, clinical trials, reviews, and all of those things. So, how and where bioinformatics or computational drug design can play a major role in this is where we have lead generation and lead optimization. Now, lead in computer drug design basically refers to the small molecules or to the drugs. So, how bioinformatics plays a role here is that we can actually use computer based algorithms, the data that is already available from experimental studies. We can use all of those things to identify new molecular targets, to identify new drugs through compound libraries. We can perform structure, biology, and molecular modeling. We'll learn more about this. And then we have a combination of medicinal chemistry here, which is we are combining mathematics, statistics, chemistry, and biology all together for the design of a new clinical drug. Now, all of these in silico, which means computational interventions, can cut down the time as well as the cost which is involved in the drug discovery process. The time can be limited to as narrow as 2 to 3 years, depending upon the experimental validation, which only takes in the clinical trials and the FDA approvals. Now, all of this bioinformatics work can actually be done in a very limited time. It does not involve too much of manpower as well. So, bioinformatics has a great role, and nowadays in modern day research, I mean, like more than 90% of the people are initially relying on bioinformatics and computational aided drug design before they are moving towards the experimental validations. So, computer aided drug design is actually of two different types. One is structure based and one is ligand based. What we are primarily focusing on is structure based. So, structure based will involve structures of the molecules, the 3D structures, whether it be the target, which can be your protein, DNA, or the RNA, or whether it is the chemical 3D structure of the drug. So, structure based drug design can either be de novo or virtual screening based. So, what does de novo mean? De novo would mean that you were a chemist or you were a pharmacist, and you think that you have designed a compound that might be very good, having very good properties, maybe antibacterial properties or antiviral properties or anti-inflammatory, depending on the disease you wanting to study. You have designed a new compound which is de novo. De novo means novel. So it's a new compound and you want to test it for that. Versus, in contrary to that, there's something known as virtual screening. So virtual screening is basically that you have a large compound library, I mean, which are freely available or might be your own in-house library, and there are millions and millions of compounds already available in the public databases. We'll go through some of them in the coming slides. And now you, among those millions of compounds, you want to identify certain set of compounds which are actually promising as drug targets for your study. Okay. In contrary to this, we have some we have the ligand based drug design. Now, what is ligand based drug design? Now, in ligand based drug design, as opposed to structure based, we do not have a specific target protein or a target DNA or any target macromolecule. We only have the knowledge of the chemical entities, the ligands. Now, using these ligands, we can identify a target structure. Now, how is that possible? So, based on the different set of ligands, we identify certain molecules or certain atoms or certain features of those ligands which are actually common and are entitled or will be very beneficial in identification of a target. So that is known as a pharmacophore model. So pharmacophore means that you're trying to identify certain features. For example, you have 10 different molecules and all of them have certain 5 to 3 to 5 points or 3 to 5 factors which are common. So based on those 3 to 5 points, we'll build a pharmacophore model or we will build a scaffold, and based on that scaffold, we will identify the QSAR, which is quantitative structure activity relation. So quantitative structure activity means the structure of your ligand, the pharmacophore, identifying with the activity of any known target protein, and we're designing a drug based on that. Essentially, what we are doing today or what we are studying today is structure based drug design, which is the more common method of designing drugs. So, now the first and foremost, the most important parameter before we can begin drug designing is identification of the medical area that has an unmet clinical need. So, target identification experimentally can be done by a variety of different techniques such as microarray, radioligand binding, fluorescent techniques, ELISA methods, a large number of those. But what we as bioinformaticians can do is we can identify targets from literature studies, and more recently, we can identify new and more novel targets by employing different bioinformatics techniques such as systems biology, network studies, and a lot more different prediction tools that are available that have been designed by bioinformaticians. Okay, and we again can then fill this gap between target sequences and structures, because as you know that there are a plethora of protein sequences that have been identified worldwide and have been deposited in different databases. I'm sure you must have gone through the bioinformatics databases. What we can do is we can take those sequences and predict their structures as well. Okay, so the first and foremost important thing is that we need to identify a target disease, then identify the proteins or the disease causing enzymes or the DNA, the disease causing factors, and then we move on to the ligands. Now, the ligands can be small molecules or they can be peptides which have drug like properties. Now, it is very essential for the molecules or the peptides to have drug like properties. Only then we can design efficient drug molecules. So, a basic of what we're doing in structure based drug design is target identification. That means we identify whether we have any known macromolecular structure, or we can either predict that structure. Then, on the other hand, we have hit identification. That means we either screen a small molecule database, or we have a de novo library or an in house library. Then we must have an active site information. Now, active site information you means that where do you think, or where is it known that the drug molecule is likely to come and bind to your target protein. Now, this active site information either you can obtain from literature studies, or if it's not available, then we can again use bioinformatics prediction tools for identification of these sites. After we have a combined data of the target, of the hit, of the active site, we perform what is known as molecular docking. Now, molecular docking in itself is an entire protocol which is highly extensive and is one of the most invaluable tools in computer aided drug design to identify where and how your target and your ligand will interact with each other. Okay, so let's begin with how can you identify targets, how can you obtain their active site information. So, structure availability. As all of you might have gone through this database known as Protein Data Bank, we can identify a large amount of structures that are already available in this database. Now, each entry in this PDB would be having a identifier. So we can either identify the name of the protein that we're trying to find out, or we can directly put in the PDB identifier, which is a 4-digit alphanumeric code. Okay, so one thing I would like to ask whether you all have visited these databases, or you would like me to visit and show how they work. Ma'am, if you could please tell me.
Mansi, they have done mostly, they have not done PDB, so you can go and see.
Okay, so I'll just quickly go through all of these so they have a fair
Yes,
idea of how
yes,
they
yes.
would
Just
work
an
according.
overview so that they know.
Yes, yes. Okay, fine. So, okay, for example, let's go to Protein Data Bank. This is the RCSB homepage. So let's try to search for some dengue virus protein. Okay. So now if you see, you have a large number of entries, all of which will give you some information about the dengue virus. Now it depends on which protein from dengue, because our search in this was pretty general. We've just put dengue virus. Now it gives us all the entries that have been enlisted. It will give you the protease, it will give you a different strain of dengue virus, it might give you, apart from the protease, if we find the envelope glycoprotein. So you can be specific about which protein you want, and in case you're not aware of what you want, you can just put in a general search like we put in right now, and it will give you all the entries that are enlisted. Now, if we supposedly open one of these PDBs, for example, for the envelope glycoprotein from dengue virus 2, we can identify, or we can go through all the details that have been used to identify this structure. So, first and foremost, it's important to identify which method. and what is the resolution of your protein or your target that you're trying to identify. So here we can see that it's an extra diffraction method, and the resolution has 3.08 angstroms. Now, for example, like we saw that we have multiple entries for proteases, right? So which entry is the best suits on what is your need? Most likely, we will choose the one which has the lowest resolution in terms of the number. The lower the resolution number, the higher the resolution is. For example, I have two protease proteins or two glycoprotein proteins. This one is 3 and the other one is 2.9. So I will choose the one which is 2.9. Okay, because it is more clearly resolved, the X-ray crystal structure. We further scroll down, we see that whether do we require a native protein or do we require a protein which has mutations. Then what are the number of chains that have been crystallized and how many chains do we require. Then again, you can scroll further down. These are all the annotations on your protein. You can scroll on them and you can identify what is required for your purpose. And then we scroll further down to identify, are there any co-crystallized ligands or are there any heteroatoms in the study or maybe any drugs in the study. Okay, these are all cofactors which are required for the protein, so they are there. In this, we do not see any extra heteroatom, so this means that this is only our protein structure. Now, what do we do with this? For example, the tools that we will be using for molecular docking performs everything for us within that tool itself. Sometimes what happens is that you're using a different tool for molecular docking, for example, Autodock, or you're using another online tool, for example, PatchDock. In those cases, your tools do not directly extract information from PDB. What you have to do then is you have to go to download files and you have to download the PDB format file. Now, what is this PDB format file? Let's just display and see. So, a PDB format is basically a file format in which all the information about your protein, any extra ligand, any extra molecule is present in that particular file. It begins from the header and scrolling down to all of this, it gives you all the information about how this molecule has been X-ray crystallified and what all parameters, the organism, everything, all of that information is present in here in the header part. Scrolling down, our PDB file actually begins from where we have this atom portion. So atom would mean that for all the residues in your peptide chain, for each atom, beginning from your N, C alpha, C, O, C beta, C G, all of these have a designed or a designated 3D coordinate, which is your X, Y, Z coordinate. So this is your X, this is your Y, this is your Z coordinate. So I'm sure you can understand the exhaustiveness of this file depending on, because each atom has been defined in the three-dimensional space. So if you scroll down, keep scrolling down, you will see for each residue. So this is your atom. This is your residue number 463. This is no, sorry, I'm sorry. This is your atom number 463. This is your atom. This is your N for ILE, which is in chain A, and the residue number is 61. So for 61, you have 1, 2, 3, 4, 5, 6, 7, 8 set of atoms which have been defined. Okay, it is very important for any of you to understand this PDB file before you can actually begin to play with it, to modify it, and to modify it for the purpose of molecular docking. Okay, so see the exhaustiveness of this file. For chain A, then again, because it's been co-crystallized as a homomer, you have another chain, which is chain B. So now all of these atoms also have the information of for chain B. Keep scrolling, scrolling, and scrolling down. Okay. Now then you see something as a heteroatom. Now again, when you have two different chains, there will be always a termination notation between these chains to tell you that this was your chain A. Now there is a different chain which is chain B, or probably there is a different ligand. Now the ligands are annotated as heteroatom, HTM. Now, these heteroatoms can be your cofactors. They can be any small peptides that are essential, or any metal molecules, for example, calcium or any sulfur molecule, chloride, ion, anything. They can be any cofactors, or they can be any drug like molecules that have, for example, when your protein and your drug have been co-crystallized, that times in those cases your heteroatom will also show you your drug-like molecules identified by a separate chain again. In this case, it's chain C. Okay, so you have NAG chain C, you have NAG chain D, you have fructose chain C, all of these. Okay, so all the information that is present here in chains is present like this in your PDB file. The most important identifier of your PDB chain, of your PDB file is this end. So for example, if your PDB file is missing with this annotation, at that time your PDB file will not be recognized by the software as a PDB file. So every software or every file or every it's known as a flat file. So all of these flat files have a particular a particular descriptor, a particular set which has to be essentially followed. Okay, so once we have this PDB, we know that we've got our structure. We can use this structure for molecular docking. Now, if again, how and why do we need to modify a PDB file, and why do we go through so much of pain of looking into a flat file? The reason is that computational studies are very, very extensive. You know, they take a lot of computational power to work upon, and especially when you're working with multiple proteins or you're working with millions and millions of compounds, you do not want to invest too much of computational power into it. So as we see that this PDB file has two chains, right? So firstly, we need to identify that whether or not our active site is in one chain, or active site in certain cases is in between two chains. For example, if we work upon the HIV enzymes such as HIV proteases, so HIV proteases, their active site or the catalytic site, as it's well known in published literature, lies between two chains. So in those cases, we cannot extract any of the chains. But for example, I have identified the envelope glycoprotein. The chain is in a single chain. In those cases, we can remove all of this extra information we have for chain B. We do not require this chain B. We do not want to extend the amount of time that has been taken. So we can remove this entire chain. We can open this file in a text edit file and we can remove this chain. Okay, and then again, if we have in some files, you know, there are water molecules that have been used, or there are any extra entities apart from the cofactors that are available, so we can remove all of that heteroatom information also. We can remove all of this data and we can create a new PDB file which only has the data for chain A in this example. Okay. Now, once we have this PDB file, we have actually manipulated the PDB file according to our own need. Now, based on that, we will, before we can start working on that file, we will actually have to generate a file or a conformer which is closer or more closer to the native structure that was actually obtained through extracrystallography. In that case, what we have to do is we have to perform structure processing. Now, what I was explaining in editing of the PDB file is actually your target processing or your structure processing. So you can edit the chains if they are needed. For example, in this case, the structure I'm showing here has ligands. So it has external two unique ligands. Now NAG in that case is a cofactor, so we can retain it. However, this BOG, now this BOG is an external ligand that was used for crystallization. So we can remove it. We can delete all of these heteroatoms. If you can see, there is HOH also, which means there is water also. So we can remove all of these and we can generate a PDB file only with our atom coordinates. Okay. Following that, we will have to perform energy minimization. Now, the tools that we will be using today do all of this in itself for us. We do not have to individually do it. But it is very important for you to know this because different tools have different input data and they require all of this before you can proceed for actual molecular docking. So there is another freely available tool which is known as Swiss PDB Viewer. You can use this tool to perform energy minimization. Now, why energy minimization? Because we have manipulated our data, manipulated in the sense we have used only a certain set of data that is required for working for our study. Okay, since you have changed the energy protocols or since you have changed the native data that was available, you perform a step known as energy minimization. Now, energy minimization in itself is a whole theory, and it involves a lot of different tools and methods. In this particular tool, two different tools are available, and these are all integration based tools. So you have multiple integrative cycles. It runs through energy minimization steps unless it gives you the energy structure or the structure with the least energy. So one is known as the steepest descent and the other one is known as a conjugate gradient. So you can use a combination of both of these or either of these to minimize your structure. Okay. Now, once we have our structure, our target has been identified through PDB. Okay. So now, in some cases, there are only protein sequences available. The structure is not available in protein data bank. Nowadays, you can use databases like AlphaFold to already give you a readily available structure. Before, like we were not having AlphaFold database for structures. What we used to do is we used to perform structure prediction. Okay, so now you can obtain the sequence of your protein. You have a newly synthesized protein and you've done the mass spec and everything, and you've identified a new sequence. And you want to see how your novel protein works. Now you only have the sequence. What to do? So you can use computational tools again. In that case, we have a large number of different tools available again. So Swiss model is one of the tools that provides energy based or homology based predictions. Okay, I'm not going through in too much details, but I will just show you. So Swiss model is a tool which you can use for identifying the structure. So your target sequence like A, G, N, Z, D, whatever is your, you can upload it here. You can either search for templates based on homology or you can directly build models. Okay. In cases where homology modeling is not applicable, where you have identified a very different protein and it does not fall into any of the parameters meeting the criteria for homology modeling, in that cases you use tools such as iTaser. So now iTaser will predict your model de novo solely based on how your what is the amino acid composition of your protein. Based on that, it's going to predict the structure of your protein. Now, once you have the structure of your protein, it is very important to validate your structure before you can start working on your structure. So, structure validation is the next part, which involves to going through processes such as Ramachandran plot mapping, or maybe ERAT quality mapping. All of those things you need to keep in mind. If you use Swiss model, all of these tools are present in structure assessment. You can click on that tool and it will give you the assessment of how good or how bad your predicted structure is. So this Q-mean score, which is given by Swiss model, indicates whether it's a good quality structure or a bad quality structure. Now, once we have worked upon our target protein, the next thing is whether or not we are aware about the active site. So, active site information can either be obtained from the literature. So, our literature reviews or anybody else who's already worked on it can tell you whether or not which are the most important interacting residues or what is the catalytic site. And this active site information you can actually use for molecular docking purpose. In cases where none of this is known, you can use tools like CastP, Metapocket, FTSite, or there are a lot of commercially available packages which already have their own prediction tools again. So when I gave in this input of my protein, it predicts an active site. Now, to keep in mind that most of these active sites are actually cavities or hydrophobic pockets. So it's I click on calculation and it identifies several different proteins. So one of these, which has the largest area, is shown here, and you can identify the residue numbers and the residue names from this entire list. That's how it goes upon. Okay. Now we are all set with one part of our CAD, which is target identification and active site information. The other part is hit identification. Now, hit identification means whether you have a small molecule compound library or you have an in-house library. For small molecule or screening of compound libraries, you have several databases. The most commonly or widely used among them are PubChem, Zinc, CHME, CHEMBL, which is from the European Bioinformatics Institute, or you have the Zinc database, or you have the drug bank. You have a large number of those. Now, what is the purpose of these databases? So now these databases are repositories of small molecule compounds. Either they can be natural compounds, they can be drug-like molecules, they are any synthesized molecules, any of those. You can directly input the name either of which kind of drug you're looking for. For example, okay, I'll go to PubChem and I would like to look for. We will be doing this because you. Okay, why not you guys do it simultaneously? Go to PubChem and let's search for a compound name as Nirma Shelvir. Let's all of us search for this drug. We will be working on this drug right now. So let's all let all of you just go to PubChem and search in for Nirma Shelvir. And also, I would like you guys to be a bit responsive because I'm not going back to the screen to see who's doing what. So just let me know when you're done, and if there's any confusion, please ask me. Okay, so let's click on this, and we have all the details of our compound or our drug like molecule that we're going to work upon. Okay, so this is your drug, Nirmatrelvir. So now this drug, okay, as you can read, it is one of the drugs that has been used for inhibiting the protease enzyme from SARS-CoV-2. That is what we will be doing today as well. So we will be using the protease as a drug target from SARS-CoV-2, and we will be using this as a known drug for our molecular docking purpose and to see how docking is actually going on. Okay, so you can keep scrolling down, and when you require chemical entities or structures for molecular docking purpose, you can download these coordinates in either of these formats depending on which molecular docking tool you are using, either in the 2D form or in its 3D conformer, or the tool we are using today actually requires the smiles format. So I want all of you to copy this smiles format for this drug to a text document and keep it safely. Please let me know when you guys are done so that I can proceed forward. Okay, so all of you please copy this smiles format.
Yes, they have done it once.
Okay. Yeah. Okay. So now we have taken a chemical entity and we've saved it. Now, in cases, for example, sometimes we're just trying to search for molecules based on our target protein, and we're not aware of which molecule can actually interact. So you can just put in protease, and you'll have a list of inhibitors that are available for protease. It might be protease from any virus, any bacteria, anything. Then you have to screen and further filter out what is needed by you. Okay, that is one way of identifying small molecules. Then again, this EMBL database, CH means for the chemistry part. So again, it has a large number of compounds you can take from here as well. You can download the entire libraries as well. In certain cases, you have novel compounds, their structures are not available. What do you do in those cases? In those cases, you can draw your own molecules. Now, how do we draw the molecules? So, again, for drawing, there are tools available. EMBL is one tool, Marvin Sketch is another tool, Swiss Doc that we will be using today is another tool. So, readily 2D drawing tools are available. You can draw your own structures and save them in any file format, chemical file format, SDF, MOL2, or maybe the file formats such as Smiles or Inch keys. Any of them you can use for further work. Okay. Then, Drug Bank is another very important database from where you can identify your drugs, then which targets do your drugs work upon, or any of these things. So, Drug Bank is another very important database. It has the known approved drugs, the investigational drugs, the experimentally available drugs, which are small molecules, which are still in the clinical trial phase. So all of these informations or all of these small compounds you can actually get from drug bank as well. Okay. Zinc is another very popular database that is available for downloading the small molecule libraries. So now the libraries will have millions and millions of compounds. It's not just limited set of compounds. There are other databases also. For example, there is a TCM database which is for medical plants or the natural products. So there are different libraries that you can use. Now how, and so this is what I was telling you, that if you have certain compounds that you have identified from literature, or there is a novel compound that you've designed yourself and its structure is not available in any of those databases, in that case you can perform 2D structure sketching. Okay, ChemAxon is one, Marvin Sketch, then Chemi Sketch. There are a number of different tools that are available that you can use any of these. Now, one more thing is, when you are drawing or when you are obtaining or extracting any of these structures from any of the different databases, these structures also need to be prepared before molecular docking in accordance to your own tool that you are using. So, one of the readily available tools which allows you to convert your 2D into 3D structure, because molecular docking is 3D. You remember our PDB file format had three coordinates. So, our ligand also needs to be 3D before it can be actually docked into the active site. So, we have a 2D structure conversion into a 3D structure, and one of the tools you can use is OpenBabel. So in OpenBabel, all you have to do is you have to open the file that for the structure that you have obtained in any of the input formats, and you can convert it to an output format, either in SDF, ML, or MOL, or in protein data bank itself, as is required by a molecular docking tool. So these are just the steps that you need to follow. Okay, now another very important parameter before you can actually declare that your molecule will work like a drug potentially, what you have to do is you have to identify its physicochemical descriptors. Now, the drug likeliness, as explained by Lipinski's rule, is one of the prime criteria that your drug needs to follow. So the molecular weight needs to be less than 500 daltons, hydrogen bond donors less than 5, acceptors less than 10, and your log P, which is a measure of the lipophilicity, needs to be less than 5, which means that your drug needs to be hydrophilic for it to be readily distributed and absorbed into the body. We need to work upon the pharmacokinetics, which includes the ADMET properties, as well as the different physicochemical descriptors before we can say that yes, this particular molecule will actually follow or is actually very good drug like candidate. So we need to keep in all of these parameters before we can start with molecular docking. I'll just give you a quick and a brief overview of what is molecular docking before we actually start working. Okay. So, molecular docking, as I explained you, is one of the most important parameters of computer-aided drug design. After we have all our target proteins and our ligands ready to work, we identify the preferred orientation or the pose of that one ligand molecule into our protein, into our binding site. Okay, so the main aim of molecular docking is to determine how two molecules will interact with one another, and not just the interaction, what is going to be their interaction energy, whether it's a favorable interaction or it's a non-favorable interaction. So as all of you know, as basics, any interaction should be a negative energy score. So higher that negative energy, the better the interaction is. Okay. Yeah, so drug design, signal transduction, all of those things, it's important. So now what are the factors affecting docking? So the factors affecting docking include both your covalent as well as your non-covalent forces. Most of the docking tools will tell you, the freely available ones will tell you the non-covalent interaction score, and the commercially available packages will tell you about the covalent interaction score as combined part of their algorithm. Okay, but most of the ones which we'll be working upon will tell you these intermolecular non-covalent forces. Okay, so protein like docking can be protein ligand and protein protein in case you have a peptide that you're trying to work upon, or in case you have two big protein structures that you're working upon. Depends on your disease that you're trying to identify and work upon. Again, docking can be rigid, flexible, or full flexible. In rigid means both your ligand and your small molecule have a rigid structure and they cannot move too much. So you cannot have too many different conformers or your conformational changes in the 3D space. Flexible, as the term says, that both are flexible and you can identify a large number of varied conformations. Okay, so docking, as we were saying, can be blind or guided. Now, blind would mean that you are not available or you do not know where your ligand is going to bind. Okay, and guided would mean that it's a targeted docking, that this is a particular specific site and I want my molecule to go bind exactly here. So, there are some tools that allow you to identify that, for example, patchdock is one such available tool online which will help you to perform blind docking. You just give it the receptor, you just give it the ligand, it will give you all the probable sites. But most of the targeted docking studies that we have been doing, so most of the tools use targeted docking and you have to identify a particular grid where your molecule will go and bind. So basically, docking, as I told you, is identification of this interaction. So this interaction can be based on shape, which is shape complementarity, or it can be based on some simulation studies. Let's not get too much into this, but just basic overview of, you must have heard of the lock and key model in enzymes. So we have the enzyme based on the shape of the cavity. We try to fit in a molecule within it so that they have the best interaction possible. Now, when we're doing molecular docking, it's in a 3D space, and the search algorithms are so extensive that they will not just give you one pose, they will give you multiple poses for each molecule. So, for example, I have docked this one ligand. Now, this one ligand can have 100 different poses within this cavity. Depending on how extensive I want the search to be, I can manipulate the number of conformations this molecule or this entity is going to have. Based on all of those iterations, each pose will have a different score. Now we need to identify that which is that best pose which has the best score. So that's what molecular docking is all about. It's a computational method to predict the preferred orientation, which pose is the one that has the best binding affinity or the strength of interaction. Okay, is that clear?
Yes, ma'am.
Yeah, okay, good. So, with this, we can actually begin with the molecular docking or the drug design process, as we can call it. Okay. So I hope you guys have that smiles with you for Nilma Trelve. Yeah.
Yes, we have. Yes, we have.
Yes. Okay, fine. So let's actually begin with. I want all of you to open Swiss Doc. So go to Google and open Swiss Doc. Okay. Now once we have Swiss Doc open, so Swiss Doc is a molecular docking tool. Okay. Now, in this Swiss talk, we have two different types of algorithms that are working for us. One is your attracting cavities algorithm, and one is your autodoc vena. So, autodoc vena is another very famous or widely used tool for molecular docking purpose. In case you guys need to enlist the molecular docking tools, you can use them. So, one is autodoc, one is Swiss doc, which we are currently using. One is patch doc, and in case you have certain proteins to dock, then you have different tools. You have Z doc, you have hat doc. All of these can be used as well. Okay. Again, because these are all tools and they are based on different algorithms. So if there is a study where I have 10 molecules and I'm docking to this one protein, and you say that, oh, patchdoc gives me this set of results, and but then you say autodoc gives me this set of results, need not be that they are always comparable. No, ultimately there has to be an experimental validation, but yes, filtering out through these can be very very easy, or it's very readily done. Okay. So now we have uh, we have Swiss talk, and we'll be using attracting cavities as the algorithm that this tool is going to use. Now it says submit a ligand. Okay. So, okay, let's read our task. So, our task is to perform molecular docking. Okay. So, our task is to identify natural compounds, curcumin and vidaferin A as small molecular inhibitors of SARS-CoV-2. Now, curcumin is your natural compound, and vidaferin is also ashwagandha. So, these are all natural compounds that you're trying to identify as inhibitors, because we obviously know that all of the drugs that are being used have certain side effects, right? So, most of us try to look for natural ways to cure any disease, and since SARS-CoV-2 is another very, very hot topic, so let's try to identify natural compounds as inhibitors. So the SARS-CoV-2 genome. Now this genome has a large number of molecules, as all of us are aware, right? Like any antiviral or any viral molecule would. So from this virus, because the protease enzyme has been identified as a very important drug target, we are using this protease for our study. Okay. So now what we have to do is, okay, wait, this I have already done for you, right? So we have identified that the PDB for PDB ID for this protease is 8B2T. For example, I did not tell you this. So what would you have to do is, you would have gone to PDB, you would have opened the home page, and you would have identified protease from SARS-CoV-2. Okay. And it would have given you a long list of all the structures that are available. Okay. Now then you would have to again filter according to your need what is needed. For example, if we go here as well, so it gives us the structure of this protease in complex with rufintrivir, which is again another drug that has been used. Okay, so this was one way of doing it. So now it says submit a ligand, provide a smiles or upload a mol2 file. Now how can you get a mol2 file? Now see, PubChem did not give us any mol2 file, right? PubChem only gave us 2D conformers of SDF file, 3D conformers of SDF, JSON or XML file. It didn't give us the mol2 file which is required by our SwissDoc. Let's check CHAMBL whether it gives us or not. Okay, let's click on this and let's see whether this is giving us. Linma 12 is also giving us a mol file. It's not, so mol and mol2 are two different file formats. So this is also not giving us any mol file. Okay, so in case this tool told you that you have to specifically upload the mol2 file. For example, patchdoc always requires your file to be uploaded in the PDB file format. Even Autodoc, if you run Autodoc, it will tell you to give you a PDB file for the ligand or give a PDB Qt file for the ligand. In that cases is where our OpenBabel comes into play. Okay, you can do this file format conversions from 2D to 3D forms. Is that right? So we go back to SwissDoc. We paste in the smiles that we had obtained. Okay, or you can either draw it here as well. See, this is a highly integrated tool. It will allow you to do everything in this tool on its own. I have told you all of this background in cases, for example, the SwissDoc server is not working. It's not available. What do you do? Okay. So in those cases, you need to have a background of all the alternate options that you can use to perform molecular docking. And I'm repeating again that each tool has a different algorithm. Each tool has different input parameters. Okay. So let's hide the sketcher since we don't need it. And now, or you can also click on advanced search. So you can directly search your molecules or your ligands through any of these ligand molecules from here. Okay, so this is the advantage of an integrated tool which allows you to work in whichever way, uh, in whichever data is available to you. So now preparing the ligands. Let's just click on prepare ligand. So it will tell you that whether the smiles you have entered is correct or whether the file you have entered is correct or it's not correct. So since we have a tick mark, which means that the ligand we have submitted is correct for docking and it has prepared the ligand in terms of it has done the conversion in itself. It has added all the hydrogen atoms that were left in itself. It has prepared a conformer. Okay, now comes the target. Now it says you provide a PDB ID, you upload a PDB file, or again you can use the advanced search and you can identify the PDB file. You provide a PDB file here by first identifying your compound, your target protein. You've obtained that from PDB that okay, this is the protein complex or this is the protein or this is the unique ID that I want to work upon. You note it down and you work on it. Okay. In case you are not aware and you have or you have prepared a structure, you go to PDB file choose and you can upload your own PDB file here. Okay. So now let's click on 8B2T. You need not download it, you just need to enter it and it will automatically extract from the PDB database. Okay. Now Why does the information available on PDB come here and benefit us here? How? See, remember I told you that you need to keep in mind which chains you want. Either, see, now this protein has only, let's first see the PDB file of this protein. I want all of you to open 8B2T. Okay. I want all of you to open this in PDB. As you can see, the name reads SARS-CoV-2 main protease in complex with nirmatrelvir. Okay, let's scroll down. Let's see. We have only one chain, so we can use it as it is for docking. Any external ligands? Yes. One unique ligand, which is the drug in itself. Okay, we can. Now, this information, why is this important? Why did I not choose a native protease protein, but I chose the one which is in combination with a drug? Is because I do not have to identify the active site then. The active site is already known because it's a co-crystallized drug. I am comparing any natural compounds with this drug. So I want them to competitively inhibit the binding of this drug to my target protein. Okay, that's why I have just chosen this particular PDB. I could have chosen the one without any drug also, but in that case, I would have either have to extract the information from literature, or I would have to predict new sites. That's not what I wanted to do. That's not my exercise that I want to perform. My exercise to perform is to identify any natural compounds which are better than the known drugs available for protease. So that's why I'm choosing this particular PDB. Okay. Now let's go back to Swiss talk. So since we have only one chain, we will click on select all. Okay. Then whether or not you want to keep the heteroatom. Now in our case, this heteroatom, which has been designated as OW1401, is the drug. So when you're performing molecular docking, you do not want your drug to be present with your target protein because you're not identifying the interaction of your drug with the small molecule. You're identifying the interaction of your protein with your small molecule. In case this heteroatom, like I showed you in the PDB before, like those NAG, NAM, or it was some calcium atom, we could have retained it. But in our case, we do not require this drug like molecule in our protein structure prior to docking. Now, again, to reiterate, because we are using this particular structure to identify the active site, let's just click on it to show where the grid would be. We're not preparing it as of now. Don't prepare because we want our target protein to be without the drug molecule. We're only clicking on it to identify this grid. So your search space essentially means this grid box that you can see. Okay. So this grid box is the space or the 3D space within which your any ligand molecule will take multiple conformations and identify the best pose. Okay, now as you see that this grid is outside of where your molecule is. Can you see that this drug-like molecule is outside of the search space? So if you see that if I would have taken any natural protein ID without the compound, it would have defined a search space which was different from where my ligand was. So the purpose of keeping this ID was to identify the search space. So I click on this molecule and my grid shifts to here. So you can see that the coordinates of this search space have changed. You can reduce the size of this search space if you think it's too large, you don't want it. You can reduce it to as much as you want. The lower the size of this box, the better, the faster the computation will be, because you're decreasing the computational exhaustiveness of your study. Okay, so while we have this, it's important to note down these coordinates, because when we preparing our target, we will be removing this molecule from our study. So it is 19 minus 14 and minus 21. Okay, now what we do is, let's just unselect this, and when we go down we see that the box is still there. Okay, okay, so we have defined the search space, we have removed the heteroatom because it's a drug like molecule. Okay, one second. Now let's just click on prepare target. So now what this tool is doing is, in preparing the target is, since we have removed the heteroatom, the minimization, remember I told you to we can do through Swiss PDB. So all of these algorithms are running in the back end, and they have prepared your target prior to molecular docking. They're not showing you all of this, but it's important as a bioinformatician, if you wish to work on it, you should be aware of all of these tools. Okay. Now define the search space. Our search space has already been defined based on that drug-like molecule. Okay. Parameters. Now parameters in this case is number of RIC. So RIC is randomized initial confirmations. Okay. So what randomized initial confirmation means? So when we are performing molecular docking, as I told you, algorithms can be different. So algorithm in case of patch dock, for example, is based on shape complementarity, like that lock and key mechanism. In this case, it's based on simulations, a number of iterations. So it will have a seed structure from where it begins to prepare the confirmations, and the more number of different random sites I give, the multiples of the confirmations will be more. When this tool was designed, the best number of RIC was the minimum. So it's kept to 1. Okay. Show extra parameters. Sampling exhaustivity. How many samples or how many conformers do you wish to identify? So let it be to default as medium, before, because if I increase it to high, it will take it will take much higher time to do. Again, cavity prioritization. So cavity means your pocket, your hydrophobic pocket. Should it be buried? Should it be medium, or should it be shallow? The more buried it is, the better it will be, because most of the binding sites are hydrophobic inside the proteins, and they are not exposed. So let's just keep it to buried. Okay. We again click on check parameters. I hope all of you are doing it side by side. Okay. Now once all our parameters for a docking are set, your ligand is set, your target is set, your search space is set, all your parameters are fine, you can begin docking. So you can enter your email ID in case you need for future reference. You can enter your docking name to enter is also important because it keeps in mind which all which molecule you've docked when. So let's just name it N and P. Okay, and just click on start docking. So now it's showing that your calculation is running, and it'll give you a result once it's done. I hope all of us are on the same page and we are running the same exercise.
Yes, ma'am.
Okay, great.
Ma'am,
Yes.
ma'am, while I was doing it, the option two, I have to check once. Prepare target is not showing, even though I have chosen like the chains as you told, the chains and heteroatoms. Prepare target option is not coming as red.
Mansi, can you respond to this question? Hello. Okay, Sarina, just wait. Maybe
Okay, ma'am.
when she responds, then you can again ask the question.
Okay, ma'am.
I'm sorry, just a second. Yes, please. Can you repeat?
Yeah, Mansi, there are certain
Yeah, yeah,
queries.
please tell me.
One from Krati, she's saying that my parameters are showing wrong. And Sarina, you can again ask your question.
Ma'am, when I was doing like what you were telling on this meeting, in
Hmm.
to submit a target, the option of prepare a target was not coming as red to me, even though I did choose the chains and heteroatoms as per you told on the meet. So तब भी prepare
Um,
target का option नहीं आ रहा.
can you once share your screen? Maybe we can see what the error is.
Okay, ma'am.
Yes, I'll stop sharing. Meanwhile, the job is running. Okay, share your screen. Let's see what's the error.
Yes. Ma'am, is my screen visible?
Yes, it's visible.
Ma'am, I chose
Okay.
this.
Yes.
I chose this,
Okay.
and it's
Okay,
still
no,
not
no. See, see.
showing prepare target.
Go back to choose heteroatoms.
Yes, ma'am.
Go down. Uh, deselect OW1. Just select none. Yeah. Now click on OK. Now scroll down.
Yes,
Okay, the box is fine.
yes, ma'am. That was
Still
the
not
problem,
showing.
ma'am.
Can you just once can you go to reset target?
Submitted our
No, no,
reset
no,
target.
reset. Yeah. Can you enter the file again?
Yes, ma'am. Ma'am, what was the name, ma'am?
It is
AP2T.
8P. Yeah. T. Yes. Okay, now change to keep. Just click on A, this one. Yes, click on A. Okay. Okay, choose heteroatom. Go to none. Click on none. Okay. Okay. Uh, why is it not showing? Can you define this? Can you just scroll down? Your protein is showing, right?
Yes, ma'am.
Okay. Not sure why that's happening. Can you scroll further up? Okay, and it's showing none again. Mm, okay, I'm not sure why that's happening. That shouldn't happen.
Mama also
I
like restarted and tried
Yeah,
to
yeah,
like save
maybe.
the
Yeah.
file again, but it was still showing the same.
I was also suggesting the same. Maybe you can log out, and start it all over again. Maybe that can help.
Okay, ma'am, I'll do that.
Yeah, just try. I mean, there shouldn't be any error with this because you're choosing the right parameters. Somebody else who was getting wrong parameters, are you done or is it still showing?
Participants, please respond.
Anybody, somebody else also had a query, no?
Prati had this problem. Prati, is it solved now? She's saying
Okay.
yes.
Yeah, okay, fine. Okay. So
Okay.
anybody else? Any issue anybody else is facing? Okay, nobody. So I'll share my screen then. And since all of us are running the same thing, so it might take some time for some of us, okay? I hope all of you are able to do it. If anybody has any problem, you can share your screen. We can just try to resolve it. Okay, so how many of you got the results?
Participants, please respond to the question. How many of you may I know?
Because it will be better if we
One,
see it together.
one student, Arshia.
Yeah, I think that's because we're all running it together, so the server tends to slow down.
Maybe, maybe.
Yeah, so that's the reason. It's okay, we can wait.
There are a few students who have got, 3 or 4 students they have.
Yes, we can wait for another 5 minutes so that most of us have it, and then I'll explain.
Sure. So, do you want to take break after this? Maybe a 15 minutes break?
Ma'am, are you asking me?
Yeah, I was
No,
asking.
no, I am okay. If the students want it, it's fine. I am okay, no problem with
Okay,
it.
I just students, do you want a break right now of 15 minutes in between, or we can continue? Okay, so Priti, we can. Okay, ma'am, continue. Let's end this exercise. Okay, after we are done with this, we can take a 15 minutes break once.
Yeah, sure, ma'am, sure.
Sure.
Ma'am, we can just take a 5 to 10 minutes break because in any case our results are coming. So
Okay.
maybe around 11:45 we can come back. 10 minutes.
Yeah, sure. So we
Yes,
can take break now since they are also doing. So
yes.
we
Since we
can
are anyways
meet.
waiting for the result only.
Yeah. So we can meet at 11:45.
Sure, ma'am.
Okay, so participants be here by 11:45.
हाँ मैं फिल गेट, हाँ गेट तो ये पहले लता मैडम से बात करनी होगी या इसी से डायरेक्ट करें? हाँ नहीं नहीं कोई बात नहीं, कोई बात नहीं, मुझे नंबर भेज दीजिए। हाँ हाँ और ऐसे ही होता है, कोलेबोरेशन में इसमें ऐसे ही होता है। हाँ बहुत अच्छा, क्योंकि बीच बीच में कुछ कुछ आ जा रहा है, बट सिंस इट इज इम्पोर्टेंट सो इसका काम जो है ना नहीं हुआ था। हाँ बेटर है, तो उसे पकड़ना मुश्किल है और कुछ शायद उसको वैसे मतलब उतना ज़्यादा ना वो नहीं आर्टिकुलेट कि आप ये भी करो, मतलब उसे पूछोगे हाँ हम कर लेंगे उस टाइप से। क्योंकि ये काम जो है ना, अब जैसे देखो इसने जैसे वाटर मॉलिक्यूल निकाला तो वैसे निकालना है वो नहीं पता चलेगा ना जब तक आप नहीं करेंगे। तो हाँ ज़्यादा अच्छा, हाँ ठीक है मैं करूँगी, मेरे को नंबर दे दीजिए इसका। अच्छा आपको जाना कब है, कल जाना आपको? अच्छा आज ही जाना है? कोई बात नहीं, इससे तो रिकॉर्डेड है ना, तो आप सबमिट कर सकते हैं। ये तो मैं डाल देती हूँ इसमें, मैं इसको डाल दूँगी, कोई बात नहीं, मैं इसको डाल दूँगी। एक जैसे हमेशा इसमें आता है ना, अगर मेरी से रिक्वायरमेंट होती हो ना, क्योंकि ये हाँ क्योंकि ये जब भी हम रामानुजन का करते थे ना तो वो दिए थे एक, पता नहीं मतलब मे बी जिस आगे कभी मतलब पड़ जाते, तो वो एक ही क्वेश्चन करूँगी मैं। नहीं मैं डाल देती हूँ, कोई वो नहीं है, आपने दे दिया ना मुझे। हाँ वो एक ही उसमें आ जाता है, मैं देखती हूँ कैसे आता है, जैसे वन टू मतलब एक के बाद और वन टू थ्री। कौन सा कौन सा कौन सा? ठीक है ठीक है। अच्छा इसमें ना मैंने नेम एंड एफिलिएशन मैंडेटरी नहीं थी इस वाले फॉर्म में, मैंने हेलो आ रही है आवाज? नेम एंड एफिलिएशन ना मैंडेटरी नहीं था तो वो मैंने मैंडेटरी कर दिया है, और जब नहीं और क्यों, क्योंकि उसमें हम लिख देंगे कि इसमें जो नाम और एफिलिएशन लिखेंगे वही सर्टिफिकेट में आएगा, तो हम इसी से लिख देंगे, ठीक है? और
Hi, is everyone back?
Yes, ma'am.
Okay.
Yes, Mansi, we can start.
Yeah, have you got the results?
Few of the students has said yes. Arya has got yes. One more. So
Okay.
few students have got the result.
Okay. Otherwise, the rest of you can see your screen. So now our Swiss doc results look like something like they tell you the input. So they tell you the smiles of your ligand, your target, your method, and when you have performed along with your parameters. Okay. The ligand tab is still loading. It will just show you your ligand structure that you have input and the various parameters you can perform with that. And till it's loading, fine. Otherwise, if it doesn't load or if it loads for anybody else, you can share your screen later and we can see. Now let's go to see how our docked complex looks like. Now what we can see here is only our protein molecule, right? So this is your receptor, and when you scroll down, you have a number of rows which are showing you the different clusters that have been identified. So the number of clusters is 10. If you wish to select if there were more, you can highlight more. Let's just stick it to top 10, and they tell you how many members were there in your clusters. Now again, the members depend on the RIC that we had input in the parameters. They tell you the AC score. Now AC score is again different for each conformer. Now this score is specific to the method that we're using here, which is attracting cavities. Had we used a different protocol, we would have got score calculations based on that protocol. And we have something here which is the Swiss param score. Now, this Swiss param score is actually what I talked about when I was showing you about the molecular docking intermolecular forces. So, this is a sum total of all the different interactive forces that we can actually see. Now, let's just sort it. I think yeah. So, we can just sort it according to the most negative score. And when we click on this row, see, it has highlighted our molecule and the different interactions. Now it's highlighting the hydrogen bonds in blue, if you can see. If I remove this, the bonds are gone, right? So this, if you hover around, is your ligand, which is colored according to the elements. Okay, this is your histidine molecule with which it's interacting. This is your methionine with which your ligand is interacting. It's showing you all the hydrogen bonds. So histidine is interacting with here. We have an ionic interaction, if you can see in yellow above here. Okay. Do we have any cation pi? Yes, we have a cation pi interaction here. See, if you see here, you'll have to zoom over and see there's a cation pi interaction showing in between. All the hydrophobic contacts, it's showing in gray. And we have pi stacking interactions also. So pi stacking interactions are usually with the benzene rings. So if your molecule has any benzene rings, it will show you that. So all these different intermolecular interactions, their sum total is shown in this Swiss param score. So the score for our drug-like molecule, the best score among all the conformers is minus 9.3629. Okay. Now okay, again, I would like to repeat that this molecule or this visualization that you can see here is essentially because this tool is allowing you, it's integrated with a visualization tool. For some cases, like maybe you're doing some online tool or something like that, some other tool, it's not giving you these interactions. Then how are you going to visualize? So there are visualization tools. So JMall, PyMall, all of these are visualization tools whereby you can visualize your interacting proteins. Chimera, for instance. Okay. Then what you can do is you can download all your results in your zip file, and once you have downloaded, you will have a folder which will give you results like this. Okay. So now it's given me the results. It's given me one second, the PDB poses. You can download all of those and you can visualize in different tools such as JMall. I'll show you one, right? So you can go to file here and you can open wherever the location of that file is, and it will show you the docked complex. Okay, wait, it's not showing in here, but I'll just open a PDB and show you how it looks like. So it will show you a protein complex along with your dog lichen, somewhat like this. You just have to download it from here, download the zip file with all of these members, and when you extract it, it will give you PDB files of those complexes. Okay. Now I want you to go back to SwissDoc and run the same exercise for A curcumin and B vidaferin A. So you'll first have to go to PubChem. You have to extract the structure or extract the smiles for curcumin and vidaferin A, and then you can do the docking. Okay. I have opened this for you. Yeah, so you can go and get curcumin and vidaferin A. Get the smiles and run the docking. Let's do for curcumin first. Let's go to PubChem. Let's search for curcumin. We've got the smiles in here, and let's get back to SwissDoc. We can copy paste the smiles. So let's choose the chain. We do not want the heteroatom. Done. So let's take the box center parameters from here, 19, minus 14 and minus 21. So let's keep it to 19, minus 14 and minus 21. Right? Okay, done.
Ma'am, I
And
had a question.
I'm sorry, I can't hear you.
Ma'am, I had a question.
Yeah,
Ma'am, how do you determine the search space, like the coordinates?
yeah, okay. See, you remember I told you that the protein target we have chosen in this case is 8B2T. So we are here in PDB, right? So what does this tell you? This complex tell you? It says that it's the SARS-CoV-2 main protease in complex with nirmatrelvir. So what is this nirmatrelvir? When I had chosen the disease COVID-19, I had done a literature search. Okay, so when I'm doing my literature search, I am identifying the target proteins. So when I've identified protease as my target protein, I try to identify, is there any known existing drug for this protein? Yes. So the literature tells me that yes, there are multiple, among which one of them is nirmatrelvir. Now I go back to PDB and try to identify whether there is any structure of protease with this drug, or whether there is any structure of any protease with any known drug. If I have it, yes, good. That is the binding site itself. Okay. If a known drug is not available, or if in literature any catalytic site for protease is not available, then I will go back to prediction tools. So these are binding site prediction tools. You remember I showed you CAST-P and all of those?
Yes, ma'am.
Yeah. So that's how you identify. Okay. So when you
Okay,
go to
ma'am, got it.
search, yeah. So when you go to search space, you remember we clicked here on that ligand molecule, so the grid box shifted, right?
Yeah, yeah.
Yeah, so that's how you identify the search space. That's what your search space means. Where in your protein molecule you try to identify the hydrophobic cavity. Okay, I'll show
Okay,
you
ma'am.
here also. See, so when I had given this protein, this is some other protein, and I had hit click on calculation, it identifies different pockets. So one is here, one could be here, one could be here. So based on the largest surface area, which means the most hydrophobic cavity, I have identified this one as the pocket. And based on this, I can identify, based on these residues, I can select the residues here. And based on that, I can define this search box cell. Okay?
Yes, ma'am.
Yeah.
Understood.
Okay. So now we're docking for curcumin. I hope all of you are doing it. Did this ligand tab load for anyone? If it did, can you please share your screen? I would like to show you how Swiss ADME works.
Who want to show? I can make them presenter.
If it's open for anybody, please tell. I'll stop sharing meanwhile. Our results are coming. And then we can see how Swiss ADME works because I would like to show you that. Nobody?
Anyone who want to? Asha is saying it's still loading. Any other who has got? They can
Okay.
share the screen.
Yeah, in case it's opening for anyone. Okay, if it's not loading, then what we can do is we can just usually when you have your result, you have your ligand here, and you can just click on this Swiss ADME, send to Swiss ADME. So it directly links it here, and all your calculations are done. Since it's not loading, let's just click in here. Let's take Nilma first, and let's see its parameters. So I'm entering the smiles here, and I'll click on run. Hopefully it should. Let's see. Okay, yes. So that's what your ADME properties look like. So it begins with the physical chemical properties, the molecular weight, number of atoms, number of rotatable bonds, hydrogen bond donors, acceptors, molar refractivity, polar surface area, your lipophilicity parameters, your water solubility, pharmacokinetics, as I mentioned. So, all of these CYP enzymes are actually involved in metabolism. This is your absorption. This is your blood brain barrier in case you're designing drugs for neurodegenerative disorders. Then again, the main parameter that we look at is the drug likeliness. So is it following the Lipinski's rules? Yes. So there are no violations for the Lipinski's rules, which means that yes, our drug is following the drug likeliness parameters, and therefore it can be considered as a good drug. Okay. This was for already an already known drug. Okay. Now what if I paste my curcumin here? Let's see. So okay, let's try to run for curcumin. Okay. Now see. Again, its physicochemical properties, lipophilicity parameters, and the pharmacokinetics. See, we cannot use curcumin for any of the neurodegenerative disorders because its ability to penetrate the blood-brain barrier is not showing. That means it will not be a good candidate for designing any of like Alzheimer's or Parkinson's, any of those kind of diseases because it's not being able to penetrate the blood-brain barrier. But does it have any drug-like properties? Yes. It's following all the Lipinski's rules. It's following other parameters such as the Gauss parameters, the Weber parameters, and all of those. And it also has a good bioavailability score, which means that yes, it can be used as a natural alternative to any of the drugs available. Okay. So it's very important to check all of these parameters before you can actually declare your molecule as a drug-like candidate. Similarly, let's do it for vidaferin also. Let's check. So let's okay, I already have it. You will have to obtain it from PubChem, the smiles, and just paste it in here. And let's just check the parameters. See again, it's following the physical chemical properties and it's following the drug likeliness properties for Lipinski's. If you hover around it, it will also tell you which properties it should follow. But again, in that case, it's not following the blood-brain barrier, which is okay, which is not our target. We're trying to design an antiviral, so that's okay. So we can use it for its antiviral properties. Okay, that's what Swiss ADME tells you. There are more different tools here. For example, Swiss Biosteer or Swiss Similarity. So this will tell you, like I was talking about, the ligand-based docking. So that is a ligand-based drug design. You can use this tool for that. And Bioisosteer will help you identify any similar compounds or any known natural or any known existing molecules which have similar pharmacophore-like properties as your known molecule, which we were again talking about in the ligand-based drug design. Okay, let's go back to see whether our curcumin has stopped. It's almost done. Let's just wait for our results. I hope everybody is now able to run it. Any of you who were having issues before have been resolved. Okay, I've got my data. How about the others? Have you got it?
Maybe Mansi, they are taking time. You can go ahead with it. You-
Okay, fine. I'll just try to explain you. Okay.
Yeah, yeah, sure.
Yeah. So let's go down first to see how our curcumin conformers have performed. So if you sort them according to the Swiss Param score, you see that the highest energy or the most negative energy is minus 7.7, whereas for Nirma-Trelvir, we had minus 9.3. So now in our study, we are using Nirma-Trelvir as our control. Like when we perform any experiments, we use a control, right? A positive control or a negative control. So this is our control compound or a control ligand that we're using. In comparison to this, our compound curcumin has performed a little lesser in terms of the interaction score, which is only minus 7.7. Okay. Now let's again try to identify the different bonds. Okay. Okay. So now again you see the difference in binding, the difference in terms of interactions. If you see the interactions here, you'll see so many contacts in between your ligand and your protein molecule. Whereas when you're comparing with curcumin, you see there are a fewer number of interactions. So primarily based on the number of interactions, you have this score. So your score is validating the number of interactions which are visible to you. Okay. Now let's try to dock our third compound and let's see how that performs. Okay, let's just quickly do it. Let's just see how bidaferrin performs. Always ensure you're using the same parameters. Okay. So here we saw the one which has the highest. Maybe let's select some other conformer just to see how it's performing with maybe a lesser score. Let's see. The interaction energies. See, they will always vary in terms of the contacts. And most importantly, the hydrophobic contacts and the hydrogen bonds contribute to the stability of the protein ligand interactions, which contribute to this score. Okay. Again, I'm sure you can see how cumbersome this entire process is. So, for example, just imagine you have a million compounds to screen. So it's not possible for you to use a tool like this in which you have to give one input and one ligand every time. In those cases, you need automated tools. So like there is one version of Autodoc which is known as PYRX. So that will allow you to perform virtual screening. So, what is meant by virtual screening is that you have a large library of compounds and you can input one target protein and you can put in probably like hundreds or 200 compounds all together. It will dock all of those and dock each conformer, rank it, and based on that ranking, like for example, you have cluster number 1, 5, 2, 3 here, certain number like this is your curcumin, this is your bidaferrin, this is your control. For all of those and for all of its conformers, it will give you an entire Excel. So then from that, it's easier for you to select the one which has the most negative energy. Did you understand? Instead of showing result for one, it will show you for all of the compounds that you have used. So that's known as virtual screening. And there are commercially available packages such as Schrodinger or such as Biovia, which allow you to perform virtual screening for millions of compounds. Essentially, they run on GPUs and supercomputers because it's very, very extensive. And in those cases, you can perform a large number of filterings also. For example, like in our lab, we used to use Schrodinger, which, for example, if I'm using for one protein, I'm using 1 lakh compounds, I'll filter it so that on the next step, I have only 10% of those best compounds. And then in the next step, I'll again filter it so that I have 10% of the previous ones, so that when the final energy calculations are happening, I have an approximate number of only the best 100 compounds. So, it's a very, very extensive process, and it takes time, firstly to perform, and secondly analysis. Analysis is very important in terms of what kind of interactions are showing, what kind of interactions are actually viable and present in your compound. Based on all of this data, you finally get down to, one or two molecules, and it takes a large number of screenings. It's not just that, it depends on what type of protein you have chosen for docking, what is the active site you have chosen. So all of the parameters are very, very crucial when you're performing molecular docking. Molecular docking is the last step, but the input that you give, all your docking results are essentially based on that. Is that clear?
Yes, Mansi.
Yeah, okay. So we can probably just wait for 2, 3 more minutes for this. All I want to show you is that, it's not very important. We may, I don't know what result we're getting for this. So we have a known compound, and we may have some compounds which are very, very good, I mean, which have a very higher score as compared to our control. But when we go back to experimental validation, they might not show good in vitro activity. Whereas if there are certain compounds also which have a little lesser score, they might show up to be very well. Or in case they may have comparable energies also as compared to the known drugs. So you have to keep in mind all those parameters while you're performing molecular docking. And again, in the end, experimental validation is the key before you can actually state it to be there. But again, without bioinformatics, screening of a large number of molecules is not possible. So yes, these tools are highly invaluable. Have to go through these, and most of the researchers who've been working lately are first performing docking studies. They are performing in vitro prediction, in silico predictions, and then going on to in vitro assays. So let's just see what this gives us. And similar to ligands, small peptides can also be docked. In this case, in Swiss dock, I don't think they will take, but if you wish to dock a peptide, patch dock, but usually that server, is not very responsive. Otherwise, earlier, it was a very good server which was freely available, and you can dock enzyme and small inhibitors. You can dock antibodies with the proteins. You can dock small peptides with your proteins. So that also works. See, essentially, when you're performing docking, if you take any ligand, it will dock to your molecule and it will give you some energy. The point is to understand the interactions and whether those interactions are actually correct depends on your literature knowledge. So you have must always correlate and must always check the interactions before you can actually proceed and say that yes, this is the best pose. Another thing, I could show you the different poses actually. So this is one. If I click on the next one, so it's an altered. Let's just try to hide all these points and show you the poses. So is one pose. If you see, they're all in the ligand is in different poses. Click on both of them together. See, I can't zoom it somehow, but maybe in a cavity you can see. They're in different conformations, and that's why they're interacting with different residues, and that's why they have a different score. See, and you can see that it's in a cavity. The protein surfaces help you identify the cavity. So all of this dark purple is actually the exposed area, but the light purple is the cavity. See, can you see? So cavities. So we should soon have a result for Vidaferin A also. Anyone else tried for Vidaferin A? And as I told you, you can again resize your box depending on the size of your molecules. If you have very small molecules, I intentionally tell you to reduce the size because it will reduce the computation time. And if you have big sized ligands, you can increase the box size. So again, all depends on your study, your parameters, and how you wish to change them. Okay. So for this also, we see that our Vidaferin is also minus 7.7. And again, the different interactions in here are clearly visible. So we have a control. Our control is minus 9.3, and both our natural compounds are lower than that, which is minus 7.7 and minus 7.76 and minus 7.73. Okay, no problem. So this is a virtual screening in which we're trying to identify whether or not they are performing well. The only advantage we have with our compounds is that they are natural products. So definitely they will have least side effects when you're using for treatment. Now, since we know that okay, the two of the compounds that we had chosen are not working, they're not giving us comparable energies or are lower, we can go and identify newer compounds. So then we go in for searching new, more natural products which may have antiviral properties and which are better which are better and which might be more strongly interacting with our protein. So then again, you can go and identify in TCM libraries or any of the other libraries in which it's needed. So curcumin and Vidafaren A have reported this. We can check if there are any higher values in any other cluster, but I'm sure not because we have identified the best 10. And that's how we can go about identifying the best compounds for our protein, for our drug target. And that's it. And after, okay, another thing, now talking is done, everything is a prediction and it's done in a static mode. What do you do next? So, for example, sometimes, people are like we cannot do experimental studies, we do not have the facilities to do it. So what do we do in terms of in silico computations so that you can actually validate what you have done docking? So docking is a static process. Now you can take any of these best compound structures and you can actually put it for what is known as molecular dynamics simulations. I'll just quickly give you a brief of what that is. So you take your compounds docked to your target proteins and you take your undocked target protein and you compare in terms of real time how that actually works. In real time means you're actually simulating it. If any of you have heard it for over, like 100 nanoseconds or micro nanoseconds, you're actually simulating it in real time. And then you get a lot of analysis for those trajectories in real time, whereby you can tell. Okay, so for example, if I say that according to my Swiss param score, my curcumin is better than my Bidaferin A, and these two are lower than nirmatrelvir. But if I perform a molecular docking and I see the trajectories over time, these compounds need not behave in this way. So nirmatrelvir might have the highest instability index in terms of molecular uh, dynamics. Let me show you a figure so that it's clearer to understand. Okay, let's take this for example. Okay, so we plot something known as an RMSD. Now, what this RMSD means is that we have an initial structure and we have a final structure of our dot complex. So, for example, that this black line indicates that it's my target protein without any drug. Okay, then these three are my proteins with the drug molecule. So we're trying to compare that since this red one might be nirmatrelvir and this green one might be curcumin and this one might be Bidaferin A. So solely what I'm trying to say is solely based on the Swiss param score or any docking score, we cannot say that which is the best one. We need further validations, and one of the most reliable in silico validations is molecular dynamics. After we run molecular dynamics, for example, this is run for 20,000 picoseconds, so which is 200 nanometers. So once it's run for this long time, we get an RMSD plot, which is a convergence plot, and we can actually compare which is performing more. So lower the RMSD over a period of time, your better interaction is. So did you understand that you cannot completely rely only on the score? You have to check the interactions. Plus, you have to perform further validations before you can actually say that yes, this is the best one. Need not be the one having the best score, is actually the one which is also the best over a period of time. Is that clear? Is there anyone who has any confusion? I can explain again. Is there anyone who wants to ask anything?
Not yet, Mansi. You can carry on.
Okay. So, ma'am, this was about it, about the molecular docking and because dynamic simulation is not possible to really show on this system because it requires a supercomputer or a GPU
Yes.
to run on. So, basics is only molecular docking that I've already explained. And if there's any confusion or anything else anybody wishes to ask,
Okay.
I can surely do that.
Sure. So participants, you can ask any of the query if you are having, if you're not able to do anything, how small, it doesn't matter how small your
Yes, anything, any
problem is there.
confusion, anything you didn't understand, just let
Any
me know.
basic thing also you can ask. If you are not able to run it, you are not able to load it, anything, any problem. So this is a platform where you can ask any of your query or anything related to this. If you have any question, okay. There's a question, Tansi, that how Swiss parameters score predict our structure of drug.
1 second, ma'am. I'll just. Yes, can you please repeat? I'm sorry.
How Swiss parameter score predict our structure of drug.
Swiss parameter score is not predicting the structure of your drug. Your drug structure is already there. Swiss parameter score is only telling you the interaction of your drug molecule with your protein. It's not giving you the structure. The structure is told to you by the smiles. You remember? Okay, wait. See, when you inputting your smiles, you put any smiles, or you can use the sketcher. The structure is visible here. Swiss param score is only telling you the interaction of this ligand with this protein. It's not telling you the structure. You're probably not able to see the structure. That's why. Okay, wait. Like I showed you in Swiss ADME. See, you can see the structure here. So that score has got nothing to do with the structure. Your structure comes from the file formats, smiles, be it SDF, be it mol, any of those. Is that okay?
I think yes, Mansi.
Okay.
Yes, it's clear now.
Okay. Anyone else?
Anyone else who have any query? You can clarify your doubts if you have any.
No doubts?
So that means everything is clear or nothing is clear.
Yeah, I was about to ask the same thing. I
Actually, it
hope
was
it wasn't
very
very
new.
confusing because I tried to keep it, minimal yet informative. I did not
Yes,
put in too much information because I know it's for the first time.
Yes, Mansi, that's what I'm saying. That for most of them, they are undergraduate level,
Yes,
and for them it's a new thing. So maybe they will take some time to
sometime,
assimilate
yes.
it. Yeah. But since there were many of those participants who are responding in between, so I we assume that the things are clear to them. At least they have, got the overview that what are the different, tools that are available for this kind of work.
Yes. Also, I would like to reiterate that this SwissDoc tool is one such tool which is providing you everything integrated into one. For sometimes you do not have such tools readily available. Like when we were working, we did not have such extensive tools, so we had to do everything separately. So it's better to know everything separately so that different tools can be worked upon together.
And I think these tools they keep on coming and updating
Yes,
themselves. So the
yes,
basics should be clear
yes,
before you can use any tool.
yes.
I just had certain, queries, Mansi,
Yes,
that these kind of bioinformatic works, do we need to have Word like Microsoft Windows for it, or Linux is better for these?
ma'am, see, if we are working online, it does not matter which operating system we are actually using. But in cases where we have to install packages like for commercial purposes, it's always recommended that we use Linux-based systems because they are more command line and they're more based on terminals. So it's better that the GUIs or the graphical user interfaces are very less. So it's always preferable that we use Linux systems.
So if we want to do certain, maybe starting with our some bioinformatic research, and also
Yes.
the Microsoft Windows will do, or we need to
Ma'am,
have.
it will do. It will do. It's not a problem. Even like laptops. So that's the advantage of bioinformatics that one can sit at home and start performing the research. Because on laptops you can definitely run bioinformatics. For example, like I was talking about Autodoc. So Autodoc is a freely available academic tool that one can install in their laptops and use for documents. In any case, these online servers are there. But in cases where you have millions of compounds to run or you have MD simulations to run, so in those cases we need better systems or better operating GPUs. So those can't be done. But basic bioinformatics research, including systems biology also, that can also be done on laptops.
Okay, and one more thing I want to know, that most of these softwares, are they freely available or mostly are paid?
Ma'am, most of the ones I have mentioned, they're all freely available and they can be used, I mean, readily, depending on their server usage because their servers are highly occupied because they are freely available. And otherwise, the commercial tools are available, but the commercial tools are very expensive. So, only big labs have those servers and tools available. But nonetheless, I mean, for publishing your work or for recognition, these tools are used. And yes, we have also published
That's what I was asking. That if we use
definitely.
these freely available softwares, there are many softwares that are
Yes,
available and many tools available.
yes.
So does it, any case, does it, affect
Impact the
the
publication, yes.
publication?
Yes, ma'am. See, obviously, if you're comparing a commercial to academic, there will be certain kind of leverage, or they will give some kind of benefit to the commercial software because they have a very extensive algorithm that's been working. But definitely, like there's a lot of published literature for Autodoc, for PatchDoc, for HADOC and ZDoc, or ClassPro in case of protein docking. So
Okay.
yes, I mean regularly papers are being published, so there is no problem in that. Yes.
Thank you. Thank you. Participants, do you have any other queries to ask? Maybe any simple query that comes in your mind, or any question. Okay, I guess Mansi, they are too occupied with
Yes,
the session.
I'm sure, ma'am,
Just,
because it's been a long one and they had too many new things to see.
yeah, yeah.
So
So in any case, we have recorded this session. So we'll be providing, it's just for the participants. So we will be providing that so they can practice, and They can get in touch with us in case any query. Participants, you can anytime get in touch with either the experts or with us. So we'll try to solve your query as much as possible. And now I would really like to take this opportunity to thank Mansi. The session was really made for the beginners, how they can start from the scratch, and anyone who is not having any base on that, they can also have an idea and get an overview that how you can go about it. You explained very nicely the different tools and kind of a very good hands-on experience, hands-on on the techniques relating to the molecular discovery that include many things and many different softwares and tools. So thank you so much,
Sure,
Mansi,
ma'am.
and we'll get in touch with with you regarding some work that we want to do.
Sure, sure. Anytime, ma'am.
Yeah,
Anytime.
yeah.
Okay.
So
Thank you so
thank
much,
you so much,
everyone. Thank you.
Mansi.
I hope you liked it.
And
And
convey my
new knowledge
gratitude
as
to
well.
Professor Latha also for letting you, such a good expert, uh, to deliver this session.
Thank you, ma'am. Thank you so much.
Thank you, Mansi.
Thank you.
Thank you, Mansi. It was a brilliant session.
Thank you
Thank you
so
very
much,
much.
ma'am. Thank you.
Okay,
Okay.
thanks.
Thank you.